Sam. So yeah, welcome everyone to today's ISyE seminar. As usual reminder, please keep yourself muted during the talk just to avoid crosstalk, but you are welcome to unmute yourself and ask questions during the talk. We have with us today Professor Merve Bodur from the University of Toronto, where she is an assistant professor in the Department of Mechanical and Industrial Engineering, and also holds a Dean's Spark professorship in the Faculty of Applied Science and Engineering. She obtained her PhD from the University of Wisconsin-Madison and did a postdoc at the Georgia Institute of Technology. Her research interests include stochastic programming, integer programming, multi-objective optimization, combinatorial optimization, and she is interested in applications in a variety of areas, including scheduling, transportation, power systems, healthcare, and telecommunications. Also, currently, she is the Informs Optimization Society Vice Chair of Integer and Discrete Optimization. So very excited to have you, Merve. So today she will talk to us about copositive duality for discrete markets and games. So thanks for joining us, and the floor is yours.
Thank you so very much, Krish, for this kind introduction. And thank you so very much all for inviting me and joining me here today. So I'm very much excited. It's a great pleasure to be here to talk to this audience. So yeah, Chris mentioned a little bit about my background and my general research interests. And today's talk will be completely like out of that range. So it's kind of a little bit outside of my comfort zone. So I'm by no means, just for full disclosure, I'm by no means expert in composite programming, discrete or electricity markets, neither game theory, but this was kind of an interesting new research avenue for me to explore in the past year or so. So I'm pretty much excited about this work. So I would like to talk about this. And I thought it might interest your department overall, and I might maybe get some good feedback afterwards, some good ideas. So that's why, like, please feel free to just interrupt me at any time to ask any questions. I would also be happy to repeat anything if you wanna. And also I'm having today, unfortunately, some like instability in terms of the connection. So also if it freezes, also please like feel free to let me know when it's back so that I can take maybe a step back and repeat what I just said. All right, so with that, let me get started then. Yeah, today I will present a recent work on copositive duality for discrete markets and games. This is a joint work with my PhD student Cheng Guo and Professor Josh Taylor from our electrical engineering department. So here's the outline. So I will first talk about our main motivation behind this work. Then I will introduce some preliminaries on copositive programming and show how we leverage its nice properties on two major applications, namely pricing and games. The starting point of our work is this concept of economic equilibrium, which means a balanced and stable state in an economic problem. For example, we have this concept of market equilibrium where demand equals supply, and there is individual rationality, which means that no one would like to deviate from this equilibrium solution. There is also this well-known concept of Nash equilibrium in game theory, where each player in the game prefers not to deviate from the equilibrium solution. There is also this concept of, for example, this wardrobe equilibrium, which is actually a Nash equilibrium, where each player is playing a very, very small role in the game. And it's always found applications, for instance, in traffic networks. So if the economic problem is indeed convex, then the equilibrium is commonly obtained in the literature in terms of solution methodologies through this concept of
Hello. Sorry to interrupt, but we lost you, I think. Is it just me?
That's okay.
No,
is it back?
You're back.
Yeah.
Yep.
Yeah.
Okay, so I'm sure this will happen.
Maybe it might help to keep the video off for yourself just to reduce the bandwidth.
Sure, I can try, but I think it's irrelevant at that. Unfortunately, it's happening at this time of the day usually, but I will turn it off if you like.
Sure.
All right, so let me start back from this slide maybe. So if the economic problem is convex, then equilibrium is commonly obtained through this concept of strong duality. And for example, if you are solving a pricing problem in a convex market, then we can simply obtain the shadow prices from a convex optimization problem. And those are the prices that are indeed we are using as this market equilibrium prices. Similarly, if you have a game where each player is solving a convex optimization problem, there are these well-established existence and uniqueness results for the Nash equilibrium. Also, the equilibrium solution can be calculated through these so-called KKT, Karish-Tucker conditions. However, in practice, there might very well exist some non-convexities in the problem. Most notably, there could be these discrete decisions. Such problems are usually modeled, like, because I'm coming from that literature, for instance, as mixed integer programs, MIPS in short. And as we know, in general, MIPS do not have this concept of strong duality. There are alternatives, though, out there. For instance, there's this concept of Lagrangian dual for mixed integer programs, but unfortunately, they do not bring us strong duality. There are some other strong duals for mixed integer programs, such as subadditive or augmented Lagrangian duals. However, their analytical forms would be very hard to obtain. So if we want to do something with the duals, and which is going to be our motivation in this work, unfortunately, we cannot work with such duals actually for mixed integer programs. Again, our goal is to do something explicit with these dual solutions that I will hopefully motivate in the upcoming parts. So instead, what we can do is the following. We can start with our mixed integer programming formulation and make this transition to this so-called copositive convex program. So basically, the idea behind this work is to transform a mixed integer programming model into an equivalent convex program and benefit its nice properties because this is a convex problem after all. So for instance, we would have strong duality in this convex space then. And in this work, we are using a particular class of convex problems, namely copositive programs. And I will explain, if you haven't heard of it before, I will explain what it is shortly. And as such, what we can do is we can leverage the strong duality and KKT conditions coming with these nice convex programs. And what we do in this work is we use this idea and apply this relationship to two major areas, namely discrete market and game problems. So again, going back to this idea of mixed integer programming, the lack of strong duality in mixed integer programs, that actually creates challenges for discrete economic problems. For example, if you are thinking about this electricity market problems, where there are these discrete decisions, for instance, whether we should start up or shut down a generator, and in such cases, it is actually hard to obtain these so-called shadow prices. And existing pricing schemes actually, unfortunately, they are unable to recover their costs for the generators because of this concept of lack of strong duality. And if you now look at the games, on the other hand, we may also have some discreteness. For instance, some players in your system may be solving a discrete optimization problem. And when we look at the game literature, we realize that the literature on discrete games usually focuses on the algorithmic side, and they can only deal with pure integer programs. Now, you cannot have mix and match. And to the best of our knowledge, for these general discrete games, we realize that theoretical results are somewhat still missing for discrete games. So that's going to be basically our game plan. So before getting into the technical content and our particular applications, I would like to elaborate a little bit more on this non-convex energy market problem, which was our
Hello, sorry, we lost you. Lost the audio.
Was it before the slide or after the slide?
Just when you started the slide.
The next one?
Yeah, the motivation. Yeah, just when you started.
All right. Okay. Thank you so very much. So I'm very sorry, everyone, that this is happening, but I have no control, absolutely. I shut down everything at home. Only I'm using my laptop, but nevertheless, this is happening.
No
so,
worries.
All right. Yeah, just keep, please, disrupting me. That's what we'll do, I guess. So I would like to, at this point, elaborate a little bit more on this non-convex energy market problem, which was our main motivation, main starting point of this work. So with my PhD student, Cheng, we've been previously working on a power system investment planning problem, where we realized there is this vast pricing literature, but there are still some deficiencies. And what we are trying to address in this work is hopefully a little bit of that. So taking a step back, I would like to tell you why we care in the first place about pricing problems in energy markets. So they're important because energy market models, they are very widely used by both private companies as well as policymakers to make their operating and investment decisions, also some environmental and energy policy related decisions. So if we do have a good market design, then this market should be able to efficiently match the demand and the supply. However, if you look at the current pricing schemes used in the energy markets, they are unfortunately unable to recover the total cost of the generators, which creates this so-called missing money problem. As a result, for instance, for the long-term planning purposes, the generator owners themselves, they wouldn't be able to have enough incentive to invest in these necessary new generators because of this fact. So now that we are talking about electricity market, the prices there, let's talk about how the electricity prices are indeed set in practice. So they are indeed obtained like via some optimization technique, which is pretty cool to hear for me as an optimizer. So basically, usually they are obtained by using these so-called dual prices, dual variable solutions of the demand constraints in this unit commitment problem. So I will explain shortly what is this unit commitment problem in case you are not very familiar with it, and duality I will also talk about in detail. But basically the prices in practice, especially in North America, they are usually set by solving some optimization problems and using the duality concept there. So if you look at, for instance, again, the practical application, if we try to understand who's setting these prices, it is what is called this ISO, an independent system operator. So an ISO, you can think of it as this one single agent who coordinates, controls, and monitors this whole operation of your electrical power system. So all ISO pricing methods are indeed based on the concept of these shadow prices, and we need an optimal shadow price to be able to decide on these electricity prices. So in that sense, since they are all using similar concepts, they are arguably all okay. None of them can be seen as categorically wrong, but which one is better? What is the best way to determine these prices? It is still up to debate, I would say. So next, I would like to quickly overview some of the existing pricing schemes, which is again just to motivate our own work. But before that, I would like to talk about very basics. Let's look into this simple linear programming model. I believe everyone is familiar with that. So linear programs are very special optimization problems. Why they are special? First and foremost, they do have strong duality. So for instance, here on the left, we do have a primal problem, and on the right side, we do have, it is dual. And what is special about this primal dual pair is that they do have some sort of a specific relationship. For instance, if your primal problem on the left has an optimal solution with a finite objective value, then we can either solve the primal or the dual, doesn't matter, we will end up with the very same optimal objective value. Moreover, there is a relationship between the solutions. So if you give an X star solution here and lambda star optimal solution here, they're also in a very special way connected. For instance, you can write down these KKT conditions, Karışık-Integraton conditions, and this X star lambda star pair optimal solutions of primal dual respectively, they will satisfy this KKT system. So in terms of the interpretation of the dual solution, we have actually something even cooler, I would say. So the dual solution also provides us some special information of these so-called shadow prices. So what is a shadow price? For instance, if you consider this first constraint and the dual variable associated with it, it is telling you like, if you increase the right-hand side of this constraint by 1, you make this 3, 4, then this lambda solution coming from the optimal solution of your current dual, it is telling you what would happen to your optimal objective value. For instance, before making this change, if the right-hand side was 3, if I solve this, let's say I obtain Z star as my optimal value, then when I make this 3 as 4, then I know that my optimal objective value will become Z star plus lambda 1 star. So lambda 1, actually this dual variable tells you the change, marginal change in your objective function if you increase this corresponding constraints right-hand side by unit 1, right? So next, I would like to cover this basics about this important unit commitment problem from power systems. So in the unit commitment problem, basically we are trying to decide when to turn on each of the generators that we have in our system and how long to keep them on, and also how much power to produce overall by them. So here, for instance, in this example, we do have an hourly schedule on the x-axis, and here we are plotting the total generation by our generators. And in terms of the generators, you can have some different types, and each type even might have multiple generators. So here's a compact version of it is mixed integer programming model for unit commitment. So in terms of the decision variables, what we have is these U variables corresponding to whether you started up a generator G or not. And we do have these P variables. They are continuous variables corresponding to the production level of generator G. In terms of the constraints here, we have these important constraints basically about demand satisfaction. This is in vectorial form. And lastly, what we have is for each generator, bunch of operational constraints. And I'm just compactly representing them in this decision as a variable set belongs to this capital X set. So all these other operational constraints, we put them into this compact form, right? So in terms of setting up the electricity prices, even in practice, in fact, what we are doing is these demand constraints are super special. We are introducing their dual variables, and somehow, whatever these dual variables would be, we are going to use them as our electricity prices. So duals of the demand constraints in a unit commitment problem, they are the ones corresponding to electricity prices. However, what type of a dual we are talking about, right? So if you look at the problem here, these U variables, they are binary variables. So we do have a mixed integer program to start with. So there's no such thing as we see in linear programming case as duality, right? So U variables are binary. So what shall we do in that case, right? So we have this potential difficulty. So maybe the first thing that can come to your mind is simply relax these binary restrictions and let's make these U variables continuous, and let's work with the LP relaxation of the unit commitment model. And now that we have a linear programming model, we can use its duals as the shadow prices and use them as electricity prices, right? However, we know that we might very well end up with this thing called duality gap. Basically, the optimal values of this mixed integer programming model of unit commitment and its LP relaxation, they are not going to necessarily match. We will have a gap. And in fact, if we are using the LP relaxations duals to set as the electricity prices, you will observe in practice that usually that's going to end up underpaying the generators. And this has implications. Accordingly, what will happen is our generators will lack the incentive to produce. And what's going to happen is we will actually end up with less supply than demand. In other words, market will fail to clear. So that's going to be a problem. So there is no simple remedy in that sense. So in that regard, there is an extensive literature in energy markets to deal with this issue. And here are 4 of these pricing schemes from that literature, some of which actually are very widely used in practice. So next, what I would like to do is I will briefly explain the main idea behind each of those very briefly, just to again show you that how they are they're all trying to use this concept of, again, the duals. And then we will see their disadvantages, and hopefully in our new schemes, we will be able to address these disadvantages and hopefully come up with a different scheme to obtain these duals and set them as electricity prices. The first pricing scheme is so-called restricted pricing, RP in short. And this is actually the one that is commonly used in practice, especially in USA. So basically, this is used by the independent system operators in, for instance, Pennsylvania, New Jersey, Maryland interconnection, ISO New England, or in California or Texas. So these are all actually used. This scheme is used in practice a lot. So in this scheme, what we do is we have on the left, again, the unit commitment mixed integer programming formulation. We start solving this mixed integer programming formulation of our unit commitment. And next up, we get its optimal solution, let's say the star solution. And what we do next is we basically fix the binary variables. Remember, these use word binaries corresponding whether we started the generator or not. We basically add these constraints to our MIP to make it an LP, because now that we are fixing all the binary variables, what's going to happen is we will obtain a linear programming problem now, the restricted model. And we solve this restricted model, which is a linear program. And now that we solved an LP linear program, we can obtain LP duals, these lambda variables, and we can set them as electricity prices. Basically, that's what they do most of the time in practice. However, you can very well guess that this is not necessarily solve all of our problems. In this scheme, if you are using these prices, then we usually end up with generators being quite unprofitable. So we cannot recover their costs. So they will not have the incentive to contribute to our system by producing. So the second commonly used scheme is known as or not commonly used, but a traditional idea is this so-called convex hull pricing. This is a little bit on the other extreme, I would say. And by design, it ends up with being like less profit deficient than the restricted pricing scheme. So this idea is using this so-called value function of our unit commitment problem. Basically, this is parameterized by the demand. So here you give me the demand vector, and the value function is corresponding to the optimal value of our unit commitment problem when we are setting the right-hand side as this provided input. So this is parameterized by the demand. So in this idea, again, we are trying to use the duals corresponding to demand constraints. But again, this is a mixed digit program. But in this idea, what you do is you look at, you take a careful look at this value function. So here what we have is we are plotting the demand versus the value function. And basically it is this function in blue, but then you look at it as convex hull. So you take the convex hull of this weird looking function, value function, and basically you use the subgradient of this convex hull function to set the prices. For instance, if your demand production level is here, then you find this one and you somehow get a gradient information and you set a subgradient at that point as your electricity price. And the difficulty of this approach is characterizing this convex hull and computationally finding such a subgradient. It could be heavy. So that's why this is kind of one extreme.
Sorry to interrupt, but I think we lost you for a second there. We still
I think it's
can't
back.
hear you.
I think
it's back.
Okay,
Yeah.
perfect. Thank you so much. So basically this convex hull pricing idea, I was saying that it could be computationally very expensive to compute such a convex hull, or without maybe fully computing it, still find a subgradient valid at that for that convex hull. So this can be seen as an extreme that computationally we may not be able to afford. So that's why indeed we do have an approximation version of this convex hull pricing idea. And this is indeed one idea that is currently implemented by the Midwest ISO. So in this scheme, what we do is, again, we start with our unit commitment problem. But what we will do is we will basically replace these operational constraint set. Look, this was xg, but I am going to first replace it with some x tilde, and I will get to it in a second. But we will replace our operational constraints with an alternative formulation. And then we will relax our binary variables. So basically, we will not have integrated constraints. So basically, this reformulation now is going to become a linear program. So next, we will solve this linear program. And accordingly, we will get it as LP duals and use them as electricity prices. So in this, as you can imagine, this purely linear programming based approach, in order to be able to get good duals, we should be using a very tight, strong unit commitment formulation. For instance, if you are using one whose LP relaxation is close to the true mixed digit programming formulation, then you will be able to get some good duals from this purely LP-based approach. The final thing that I would like to review to give you the last option is this primal dual pricing, which is trying to find some revenue sufficient pricing scheme. So in this one, we start again with our unit commitment problem and take all of the constraints in the unit commitment, put them there. But what we do is we relax the unit commitment. Again, we just put the LP relaxation of the primal unit commitment problem. And now that we have LP, we take its dual and we also put the LP dual constraints to this one formulation. In other words, this time we are keeping both primal and dual related constraints around. And then we put our integrated restrictions back. But now that we are talking about MIP, there could very well be a gap between MIP primal and LP dual. We are in the objective minimizing this thing, the duality gap, basically, which usually helps us stabilizing the prices. And the advantage of this one is now that we are working with both primal and dual variables in this single problem, we can go ahead and explicitly include these revenue sufficiency constraints. And our main observation at this point is that this is helpful to at least have this one desirable property that all the generators will be profitable or they will not be losing money. But still, this problem also has some duality gap. So I would say at this point, if you look at the literature, all these existing ideas, our main observation is that none of these schemes are actually arguably working with the right duals. So what are the right duals? I feel like at least we have one suggestion where we will start with a model formulation which doesn't have any duality gap, so that we might be maybe working with right duals. So all these approaches, they're heavily relying on LP duality. We believe that LP duality is not appropriate for mixed integer problems to start with. So that's why our suggestion is maybe the right duals might come from these convex programs that have strong duality. And in the light of this, we choose one such class, namely Copositive Programming. So let me briefly go over the basics of Copositive Programming. So let me start with the cones themselves. So the cone of Copositive matrices is defined as follows. And basically, it looks very much similar to the definition of positive semi-definite matrices, except the fact that in the semi-definite case, here you do have real, not necessarily non-negativity there. So basically, a symmetric, so this is the set of symmetric matrices. A symmetric matrix X is called copositive if for a non-negative vector Y, you have this expression greater than equal to 0. So this cone has its dual cone, known as completely positive cone. Basically, a completely copositive matrix, any matrix from the C star, it is a matrix that can be decomposed as the product of the two non-negative matrices. So basically, you have X here, and if you can write this matrix as XX transpose, this is a completely positive matrix. And this also looks like very much like this Cholesky decomposition for a positive semi-definite matrix, if you are familiar with it. So these cones have some known restrictions and relaxations. So here what we define as these sets is this S star is the set of positive semi-definite matrices, and N is the set of the cone of element-wise non-negative matrices. And if you take the Minkowski sum of these two objects, then you will obtain a restriction on the copositive cone C. On the other hand, if you go ahead and intersect these two objects, you will end up with a well-known relaxation of the completely copositive cone, thanks to Parillo's work. So our work is actually uses this result of Samburer on mixed integer quadratic programs, MBQPs in short, which is a generalization of mixed integer programs with quadratic objectives. So this result says that a mixed integer binary quadratic program can be equivalently reformulated as a completely positive program, or in short, I will refer it as CPP. So what is a CPP? CPP is indeed a linear program, but it's over a completely positive cone. So you do have your cone constraint, but everything else, objective and constraints, they are linear on this matrix type of a variable, decision variable. And what is cool about this CPPs is the fact that they do have dual, and in fact, they do have strong dual. So dual is called COP, a copositive program. So basically, this is similarly defined as a linear program, but this time it's over the copositive cone, not completely positive cone. So we have these two linear programs in this weird matrix type of a space. So how we usually solve these CPPs and COPs? We are usually solving them by semi-definite programming approximations, as I just mentioned in the previous slide, thanks to Parillo's STP hierarchy. So here's a summary of that. So basically, what we have is we can start with an MBQP. We can reformulate it as a CPP, which has a strong dual under some mild conditions, like in existence of an interior point, whatnot. And usually we solve those problems by means of approximation. But in this work, we will propose something that is going to be exact. So now let's take a closer look at the reformulation of an MBQP. So here we have a general MBQP problem to start with, which has a quadratic objective. So this is the quadratic term, which could very well be non-convex. Also, we do have some binary variables in this problem, as well as some continuous variables. So moving to the right side now, what we have is this non-convex problem on the left. It can be transformed into a convex problem on the right, which is basically just adding this new set of variables, capital X's here, in addition to small x's. So we are basically lifting this problem on the left into a higher dimensional space. And what else we are doing is we are keeping everything on the left. And in terms of the addition of this new variable, this capital X, you can think of it as it is somehow corresponding to these X squares, XX transpose to be more accurate, actually. So in that regard, what we are doing is when we replace this XX square in the quadratic term, they do match. So the objective of this problem is exactly the same of the objective of the original problem. So objectives are equal. In terms of the constraints, we do have our linear constraints from the original problem, as well as we have their square. So we square the linear constraints and also add them to this new formulation. The best part about this, I would say, is the fact that we can get rid of our variables binary restrictions and instead add these constraints, which are somehow telling you the idea of, and if you have a binary variable to start with, any xk, then its square must be equal to each other. Using this simple observation, you are adding these extra constraints. And of course, there's no free lunch. In this reformulation on the right, unfortunately, we do have this conic constraint. And this new matrix consisting of our original and new lifted variables, it should live in the completely positive column. Okay. But note that basically this problem on the right, this new non-convex problem, it has almost everything linear. It's linear objective. It has linear constraints, except for the conic constraints. So that's the complexity. So basically what happened is all this pink complexity here, it moved to this one conic constraint, I would say. So these two problems are actually equivalent to each other in the following sense. First things first, their optimal objective values match. But if you are interested in the solution itself, which we wouldn't need actually particularly ourselves, but if you're interested in the solution, there's a small catch. Basically, if you have a solution of the original of this reformulation, let's say if this guy is an optimal solution to this reformulation, then X star may not be readily binary, so it may not be feasible to the original problem, but we know that it lives in the convex hull of our optimal solutions. So it's kind of a combination of the two optimal solutions. If you need a binary X star, you might need to do a little bit more work, but we wouldn't need that. We just need basically the first fact that these optimal objective values are the same. So this is a proper reformulation. Okay, so here's what we have is this. We will use this reformulation idea, this relationship, first on, basically here's the idea, sorry, I forgot to mention. So here's this relationship. So if you start with, for instance, a non-convex problem like a mixed integer program, we can reformulate it as this convex problem, a CPP. And it has strong duality, again, under mild technical conditions as a Copositive program, COP. So what we do in this work, this is the summary of our work, is we use this relationship first on discrete market problems and propose a COP-based pricing, new pricing scheme for electricity market. Next up, we use this relationship on discrete markets where we derive some existence and uniqueness theorems, as well as some KKT conditions for discrete games. Lastly, since both of our major applications need to solve COPs, Copositive programs, we also propose a novel cutting plane algorithm to solve general mixed integer Copositive programs. And to summarize our contribution, basically our main goal is to leverage this notion of duality for discrete problems. And in our first application, we are proposing this novel COP-based pricing scheme for non-convex energy markets, which has some interesting desirable properties. I will talk about them shortly. But it might have some disadvantages, and we try to address that disadvantage by a simple modification of this new pricing scheme. Hopefully, it will also have a nice property. And I will show you some numerical experiments to compare these approaches. In our second major application, games, we also leverage this Composite Programming and duality and KKT conditions there to derive some results for specifically mixed binary quadratic or MBQ games in short, which is a special case of discrete games. In addition to existence and uniqueness results and KKT conditions, for a very special case of MBQ games, but we are also showing that we are able to reformulate these KKT conditions into a single COP problem. And since we also have this new exact cutting plane algorithm to solve COPs, we can directly apply and obtain exact solutions there. And in terms of our algorithm, to the best of our knowledge, this is the very first cutting plane algorithm. And this is the first algorithm in the literature that can handle some integer restrictions on top of a Copositive program. All right, so before getting into the details of the applications, I would like to briefly talk about the methodology. So the cutting plane algorithm. So knowing that you guys have a lot of strong discrete optimization people, I know many of you might be already familiar with cutting plane, but I will try to still review these basic idea behind it. So our algorithm, as I said, it can solve a general mixed integer Copositive program. So here what we have is our decision variables are this omega and lambda variables in vectorial form. And this omega, it needs to belong to the Copositive form, cone. and everything else is linear. So only the conic constraint is difficulty, but also we are adding another difficulty is that some of the decision variables, they can also be integer. They might have some integral restrictions. So what we are proposing is a cutting plane algorithm, which basically decomposes the problem into a master problem and a sub-problem and iterates between the two until convergence. So how we obtain the master problem?
Merv, I think we lost you for a second. We are still not able to hear you.
Okay, it's back.
Yeah,
I can see when your video comes back. So thank you so much. So let me maybe take a step back. So basically, we are addressing this general composite program with some potential even integrate restrictions. So the difficulty is you have the con constraint in yellow and you have some integrate restrictions in red. So we are proposing this cutting plane algorithm, which decomposes the problem into a master problem and a sub problem and iterates between the two until you converge. So the master problem is simply obtained by dropping this purple conic constraint. Therefore, whatever else remains, it's simply a pure mixed integer program. And this mixed integer program, it will provide a candidate solution, and most notably this omega hat solution, green one. And what we need to do then in our sub problem is simply the constraint that we drop, this con constraint, we just need to check whether this guy that we obtained from the master problem as a candidate, whether it is copositive or not. If it is copositive, then our constraint that we relax, it's already satisfied, so we are done. Otherwise, we will add a constraint, a new cut to our master problem to be able to cut this solution off. Basically, this is referred to as a cut. That's why the name is cutting plane. So in other words, what we will do is we will refine our master problem over iterations by enforcing this conic constraint, not in one shot, but as a collection of inequalities that we generate on the fly. So I will not be able to get into details due to the time constraint here, but basically our sub-problem, this copositivity check, is relying on this very recent idea from 2020, which is basically a mixed integer programming model recently proposed. And this idea is actually the very first mixed integer programming formulation for copositivity check. And it's actually developed based on a recent characterization of copositive matrices from an algebraic perspective. And I will not be able to explain the model, but basically I will tell you what we are doing after solving this separation problem as a sub-problem. We solve this and we obtain its optimal solution, let's say an optimal value, this W bar. And if you look at the optimal value of this separation problem for your candidate green omega hat, you solve it, you get your optimal value. If it is positive, then it is actually its optimal solution Z star is a certificate that your matrix was not copositive. And we can cut it off by simply adding this constraint to our master problem. Z bar is this optimal vector coming from the sub-problem solve. And if you introduce this to your master problem, it will kill this green candidate solution, which is not copositive. And hopefully next time, master problem will return as a copositive problem matrix and we will be done. So that's the main idea behind the algorithm. Couple of comments about the algorithm. Compared with the commonly used STP approximation for composite programs, our algorithm is exact when it finishes. And it is also purely mixed integer programming based. Therefore, it can be straightforwardly implemented using MIP solvers like Cplex or Groby. While, for instance, there's another exact composite programming algorithm in the literature, which is the simplicial partition based method. And I personally believe it's not very easy, straightforward to implement. It is an iterative, like linear approximation algorithm that also has the difficulty drawback as well, which we also have, but it converges in the limit. And ours is, we also don't know whether it converges in finite time, but in all of our computational experiments where we benefited from this algorithm, our algorithm, it converged in a reasonable amount of time and a finite number of iterations, but we don't have a formal proof for this fact. So lastly, it's also important to note that our algorithm is applicable to composite programs where you might want to also have some integrity restrictions on certain variables. And this is again the first in the literature. We have a bunch of enhancement ideas for the algorithm as well, but I will skip the details. These are mostly like standard enhancement ideas, I would say. All right, so now let me just introduce you our very first major application on this pricing in electricity markets. So now I will go back to our unit commitment problem again. So again, just a quick reminder, what we were doing in unit commitment is we are making decisions about these production levels, about these generators, whether we should turn them on or off. And accordingly, on or off, the U variables will denote whether we turn them on, and Z variables will denote their on and off status. And I will get to the slugs in a second, but in the problem, again, we are minimizing the total production and this turning on the generator type of costs. And the first set of constraints, it's saying that just you need to satisfy the demand for every time period in your planning horizon. And the last set of constraints are just, these guys are just bunch of operational constraints for every generator for every time period. I just again compactly put them into this form. These set of constraints might have, for instance, some production constraints, capacity constraints, ramping up and down constraints, so on and so forth. So one thing that I would like to point out here is that it is sufficient for us to ensure that only these Z variables are binary because of the green operational constraints. Ensuring the Z being binary ensures that U variables will also be binary. So moving forward, I will only keep these on and off status type of Z variables binary. So as we discussed before, if this unit commitment problem were linear, then we could have actually directly used this duals corresponding to the demand constraints to set as the electricity prices, right? However, we have a mixed integer program here, so we cannot obtain such duals. And what we will do is we will transform this mixed integer program, as I mentioned before, into a completely positive program, CPP, and use the strong duality there. So in order to be able to use a standard CPP reformulation, lastly, we are also introducing these phi type of slack variables and turn all the inequality constraints into equalities. That's the standard transformation. And finally, this bold X in the last line of the slide will denote all of our decision variables in the unit commitment problem. So here's the unit commitment problem again, where we are making, where we have the CPP reformulation and we have again all the original constraints, but also now these lifted demand and lifted operational constraints, these squared ones, right? As well as the pink conic constraint, of course. And on the right panel, you can see the corresponding dual variables for those constraint sets. So we've seen that you can take the dual of the CPP and you will end up with a Copositive program, and its feasible set I'm compactly denoting as this F of COP. But what we really care about moving forward in the talk is what we see in the objective. So what you see in the objective, the colored ones, the dual variables, those are going to be the ones that we will include in our pricing scheme. So basically, we will include the dual variables from the demand constraints, and it is lifted counterpart, and operational constraints, and it is lifted counterpart. The rest of the duals will not appear in our pricing scheme. More formally, here's our pricing scheme, which we are calling Composite Dual Pricing, CDP in short. So in this new pricing scheme, we are using the optimal dual solution obtained by solving this Copositive program. And more formally, under this CDP mechanism, what we are doing is at every RT, the system operator is doing the following. And remember, the system operator is this agent who is coordinating.
Merve, we lost you. We still can't hear
back?
You. Yep, it's back. Thank you.
Okay, thank you. So I was saying that in this new pricing scheme, we are using the duals coming from the COP problem's optimal solution. And basically what we are doing is at every hour, the system operator will collect some money from the demand side and it will pay the supply side. So how much it collects? So in our suggestion, the system operator will collect from the load this amount of money, this amount of payment. And in this one, the first two terms are basically these payments from the demand in green, and the rest are coming from the operational decisions. And in terms of how much the system operator need to pay to the generators, here's the expression. And in this one, again, in the first two terms, we have some payment regarding the generators' production levels. The next two terms in blue, basically, they are again regarding their operational decisions, for instance, being available for you in the system, whatnot. And the last term, I will not be able to get into so much details, but it's also, again, it's about like this lifted counterpart of the production related constraints. So because of this lifting idea, we need to have this last term for the demand. So what type of properties our pricing scheme has? So first things first, thanks to strong duality of Composite Programming basically and CPP, we can prove that the system operators under this scheme, they are actually budget balanced, which is to say the revenue from the demand side, it is equal to the payment to the supply side. In addition, we can prove that for our generators, if you sum up their total revenue, it will equal to the total cost of the system. In other words, we have this thing called revenue neutrality, which is nice. These are all desired properties in a pricing scheme. Moreover, we can prove that under certain conditions, this CDP mechanism is individually rational, which means that none of the genuine generators would like to deviate from your unit commitment solution. But of course, there's no free lunch again. There's a downside. This new pricing scheme may not ensure revenue neutrality of individual generators. Unfortunately, what we have as total for the whole system, it doesn't extend directly to the individual generators. Another disadvantage I would say is this CDP mechanism is using this generator dependent prices, these blue phi and capital Phis. And in practice, we prefer not to have this type of prices because in practice, actually, we don't care about which generator produces the electricity. We just would like to use some uniform prices. They should not depend on generators. That's what is desired. So accordingly, in order to address some of these disadvantages, we are next proposing a modified version of our composite programming based pricing scheme. And we can do this thanks to having these dual variables explicitly around. Because we have a CPP and its dual COP, we have access to both primal and dual variables, so we can do something with that, most notably in this case to address some of these limitations of our first pricing scheme. So that's what we do. Basically, in this modified version of our pricing scheme, which we are calling RCDP, the revenue adequate CDP pricing scheme. So basically in this one, we take our Copositive program. This is our original Copositive program, but now we are explicitly enforcing that each generator in this pink constraints, each generator should be able to earn as much as they have their costs. So they should be able to recover their costs. So we are explicitly enforcing that they should be revenue sufficient. And again, we are able to do this thanks to having direct access to the pricing problem, the dual variables themselves. And I would like to point out the fact that this is a property that the other 4 pricing schemes, for instance, from the literature that I mentioned, unfortunately, they do not have because they can only compute some duals, but they cannot work with the duals explicitly. And our system operator under this modified scheme, it remains budget balanced. So this has also nice properties. So very quickly, I would like to talk about our second application problem for mixed binary quadratic games. So what are these mixed binary quadratic games, MBQ games basically? They are a special type of discrete games. And the classical biometrics game is an example of MBQ games. And a classical biometrics game example, you might be very familiar with it, is this prisoner's dilemma. And this game has some discrete decisions because you have this for each decision maker, they need to decide whether they will confess or not confess. So it's a binary decision. Another example of an MBQ game would be the Kuno game in energy markets, where there are these competing players and they are trying to decide their own optimal production levels. So here's the formal setup. So formally, we are defining this n-person MBQ game where we have this set I denoting the set of index of our players. And here the small vector bold xi is denoting the vector of decisions associated with player I. And this vector xi may contain both discrete as well as continuous decisions. And their feasible region of the players, they are denoted by capital calligraphic xi. So in such a game, basically, every player I is solving a mixed binary quadratic program. So, but this one is basically every player I, if you fix the player, this notation is very, I guess, standard in game theory. Minus I means what the decisions of all the other players than you. So basically for player I, if they were given the input as what the others are doing, they would like to obtain their own decisions by solving a mixed binary quadratic program. But of course, we are in this game theory setting, so we would like to somehow find a solution, an equilibrium, right? So in that regard, towards finding an equilibrium, let's define a couple of other notations. So let us call the objective function of this payoff function as f of I. And then what type of a solution we are looking for is, for instance, it could be a pure strategy Nash equilibrium, PNE in short, what is it? It is basically defined by this inequality. And it simply says that a player I, and this is true for any player I, this player wouldn't want to deviate from this equilibrium solution X star. So that's what we are looking for as a solution, an equilibrium. So with a similar idea that we've seen in the energy market application, what we can do is now we can take these MBQPs associated with our players and we can transform them into a CPP, completely Copositive program. And in this way, what we can end up with is this, we can transform this MBQ game to what we are calling a CP, a Copositive game, where now each player will not be solving an MBQ. Instead, we will treat it as each player solving a Copositive program or a completely positive program. And what we can prove is that under certain conditions, the Nash equilibrium of an MBQ game is going to be equivalent to the Nash equilibrium of a CP game. And this result actually here sets the foundation of our existence and uniqueness theorems for pure Nash equilibrium of an MBQ game. And again, as I mentioned, like in the literature, we haven't found a lot of like theoretical results in terms of existence or uniqueness of Nash equilibrium, pure Nash equilibrium for discrete games. But what I would say is now that we are playing this game of, we have our, for instance, mixed integer discrete game, and now we are lifting it into this higher dimensional space where everyone is using a Composite program or completely positive program. Actually, now that you are living in this space, which is convex, I would say this existence and uniqueness results that you have, they are direct implications of the existing results from the convex game literature. So this is nothing like super novel, I would say. It is still now that we have this perspective that we are lifting this into a nice convex space, then we can directly borrow the ideas about existence and uniqueness, for instance, from the convex game literature for our setting. But to be a little bit like more maybe formal, explicit, here what we have is these 4 conditions required for us to guarantee the existence of a pure Nash equilibrium. And some of those are actually like compactness. It is directly inherited from the existence and uniqueness conditions for convex games. The rest, I would say, is specific to our setting MBQ games. Because what we want to do is, again, we want to do this transformation. And in order to be able to do that, then this is a technical condition associated with, I'm sorry, this is associated with CPPs. The other ones, again, to be able to transform the solution back to MBQ game. And lastly, again, as I said, under very similar conditions that we have almost the same from the convex game literature, like certain regularity conditions, like Slater's condition for interior point, or this diagonal strictly convex type of a condition. If you do have those, then we will also have the uniqueness result. And I would say like this uniqueness result actually directly follows from Rosen's very popular, like very well-known result. So finally, I would like to tell you like, okay, let's say PNE exists, how we can find it, right? So one way to be able to compute this thing is to write down these system of KKT conditions for our CP game. And note that this condition, actually, if we write them down, we can do it. But unfortunately, it will have a lot of difficulties in it. So it will have bilinear terms, it will have copositive as well as completely positive conic constraints. And because of that, this system of KKT will be very, very difficult to solve. However, what we prove in this work is that if you do have this special case where in your original mixed binary quadratic programs, you do have all, I guess I'm frozen. Is it? No? Okay, good. So if we do have in our original problem, pure binary cases, every variable is all binary. Moreover, if we have only equalities, and I would like to state that this is not a trivial game. For instance, biometrics games fall into this category actually. So under this case, one special case of discrete games, what we can show is that we can actually reformulate KKT conditions to a single mixed integer copositive program. And now we have, thanks to our cutting plane algorithm, one exact method to solve this pink single mixed integer copositive program. All right, so that's what we do basically in terms of applications. Let me show you a couple of like numerical result slides to illustrate our algorithm's performance as well as our applications. So here's what we are seeing is, first of all, we are comparing our algorithm with the commonly used STP approximation on a very famous combinatorial optimization problem, maximum click problem on graphs. So in the table, what we see here is that we have the instances and bunch of instance characteristics, number of nodes, edges, and their click number, the optimal solution basically. So next up we have, for instance, for our cutting plane, we are reporting our solution time and how many iterations cutting plane algorithm took. And for the STP approximation, we are using Mosaic as the solver, and we are showing you what is the objective value of this approximate solution. It may not be exact, right? And accordingly, what type of optimality gap it obtained and how much time it took Mosaic to obtain this solution, approximate solution. So our observations is in this experiment is that our cutting plane algorithm, first of all, it is always giving us some exact objectives. By design, it's exact if it terminates, while the STP approximation can be a little bit inaccurate. For some instances here, for instance, shown in pink, it can have some optimality gaps. Also, what we observe, if you look at now these pinks, the cutting plane algorithm usually converges, as I said, in few iterations, but also sometimes it even happens to be faster than STP approximation, as in these highlighted instances. So I believe like it shows that there could be some promise there maybe, but of course we hit some difficult cases. We cannot even maybe solve one separation problem, but maybe we are in the MIP space, maybe we can have some enhancements in the future. So next up, we are going to talk about this application pricing type of results. So we test our new COP-based pricing scheme on this very classical non-convex market example called the SCART example, which can be viewed as a simplified version of the unit commitment problem, I will say. So in this slide, what we are comparing is our pricing scheme with two of the ideas from the literature, restricted pricing RP and convex out pricing CHP. And we test different levels of demand, which you can see on the x-axis. So I have different types of results that I would like to just point out a couple of findings. So if we look at the first figure here, the blue, which is corresponding to restricted pricing, what you observe is that actually this restricted pricing might have very volatile prices. So on the y-axis here, we have the uniform price. And if we actually now look at the figure below, again, the blue curve, what we will also see that actually it might also use a very high kind of like generator dependent prices. So RP doesn't play out well in that sense. And finally, if you look at, for instance, this CHP, this figure, which is about the how much extra payment you need to make to your generators so that they can recover their costs. And that seems to be high for CHP. In other words, it doesn't ensure revenue sufficiency. So that's why it needs to make a lot of uplift payments. Overall, we believe like based on these results, we believe that our modified COP-based RCDP pricing scheme is the best because it requires none of these types of uplifts and it is only relying on the uniform prices. It doesn't have anything generator dependent. So finally, we test our reformulated KKT conditions for these special biometric schemes just as a proof of concept, because in the literature, you can find much more efficient algorithms specially designed for biometric schemes. And here what we see that for these biometric schemes of sizes from 2 times 2 to 5 times 5, and we are basically reporting averages over 5 instances per row. What we find is that, again, our cutting plane algorithm converges within just seconds. But again, this is not nowhere near to the state of the art for biometric schemes. There is a special design algorithm which is much faster than solving our KKT conditions. However, again, our method is general. It can be applied to some other discrete games. So I will leave it at that, I guess. So basically, this is the summary. You can find the preprint of the paper online. We do have some future ideas, but if you have any, I will be more than happy to hear about them. Also, if you have any questions, I will be happy to stick around to answer them. Thank you so very much.
Thank you so much, Professor Bodur.